All right. Okay, thanks guys for sticking around. We're going to do the inequality, and then after that I'm going to, I don't know. We'll see how long it takes. So, 3-variable inequality, let's go! Okay, so 2 to 2 is an inequality case, but I'm curious if there's any others. Like, I somehow have a feeling that there might be more. So, wait, before we use tangent line trick, I'm gonna try some other things, because something feels off to me. So 330. Actually, let me try 600 first. Let's use. So 600 gets. Okay, you know what? I'm too tired from that China TSC problem. I'm just gonna use Python. Define f of define f of x. Return x times x minus 4 over 4 times x minus 9 times x plus 6. So for example, f of 2 is 0. Okay. 6 plus f of 0 plus f of 0. F of 3, that doesn't work. 3. Yeah, okay, 3 to go. See? And f of 4, 1. We're not. No. How did I break? Oh, I forgot a dollar sign. F123. Okay, so at least 123 is not an equality case. If 123 is an equality case, I'm really scared. So 600 fails is equality. 222 is equality. So okay, that might explain why this one is 6, because that's necessary to yeah, 330 is equality. 222 is equality. Are there any ones? F of 411. I think is the other one I want to try. Okay. Alright, so that's a cursory start. So we at least know this equality both at 3 and 2. So you can't. Tangent line trick is promised to not work. Unless the function like has a tangent at both like 2 and 3 or something ridiculous like that. That's fine. Yeah, I wanted to fish this out because from looking at the constants, I had a feeling that there's probably more than one equality case. Constants are too artificial otherwise. Are the denominators ever negative? I want to say no, right? So a squared minus 4 over 2a yeah, so tangent line will never work. I'm a little surprised. Is 4x squared minus 9x plus 6 always positive? It is, right? No, it's not. B squared minus 4ac. So denominator is sometimes negative. That's really annoying, actually. What are the roots? Wait, that's very surprising, actually. Because the problem seems like it shouldn't even be well-formed in that case. So if, what are the roots of this thing? It's x equals 9 plus or minus. No, that's fine. Sorry, my bad. Discriminant's negative. Alright, we're all good. Everything's fine. It's minus 15. Okay, alright, that's fine. So what can I do that has equality at both 3, 3, 0 and 2, 2, 2? Yeah, discriminant's negative. I was just being stupid. Oh wow, okay. That's actually a pretty big hint that the exact constant there doesn't really matter. I had to reverse engineer two equality cases. Yeah, you don't want to let k equal 0. Alright, so I want to make things positive so that I can stop confusing myself, so I'm going to do that. I'm going to multiply both sides by 4 and then subtract off 3. So 4a squared minus 16 minus 9 minus 22. So something like that? Did I do that calculation correctly? Oh, sorry, at least 3. So no, I definitely didn't do that correctly. So it's 4. It should be 10. 9a plus 10. No. Oh my god. Help! 4a squared minus 16. No. Hang on. Okay, what's the transformation when I do it? It's like... God damn it. So it's minus 4a squared plus 16. It's 22 minus 9a. That's not good. That's still not positive every way I want it to be. Actually, that's actually not much better. Do I want like 4a squared plus 28? Feels a little unnatural to me. Okay, so a squared plus 7. Alright, cool. That makes all of the denominators, all the numerators positive. Did I make a mistake? I think I made a mistake already. Crap. 22 minus 9a, and then I add. Oh wait, I'm just plotting. Oh crap. Oh, come on. Okay, here's a different question. Is there like a multiple layer cake theorem? Three, 3, 0, and 2, 2, 2. Alternatively, I could just expand. Alright. Does n minus 1 EV apply? Like, is this function have exactly one inflection point? Oh jeez, I don't want to compute this. Inflection between 2 between 0 and 1. Oh crap. Okay, well. That goes out the window. 'There's no function in A that I can bound the fraction by, right? Like is there a way I can bound each individual fraction? I want to say no. Is there, like, there's no polynomial for which... Well, if I have a quadratic polynomial, actually, 9, 18, 4, 8, 12. Like, is there some polynomial for which I can... This is a stretch. I don't think this is possibly gonna work. But... freaking this is so desperate. Do I think this could possibly work? I don't know. Wait, right? A equals 2 says that if I want this to work, this constant has to be minus 2/3. Then by plugging in a equals 2, the other constant has to be like... one-third. Plug in 3. 1/3. Oh, actually this might work. When I plug in a equals 3, I get the right thing. But actually... do I even need the trailing thing? No way. Really? No, I don't believe this. This is too good. Yeah, this is too... Really? Maybe I just lop off this bit here? Is that true? No way, right? Yeah, there has to be some correction term. I am surprised because when I plug in like a equals 0, 2, 3, it is a equals 0. Maybe I don't need it for 0. Yeah, when I plug in a equals 0, 2, and 3, it does actually get the right thing. So the linear part is correct. Okay, so if I want this to work, um, well, either way, something is up. Because that function, like that linear function, matches the fraction at like literally 3 points. So no matter what, I think it means it justifies me like clearing the factor of 3 and looking instead at the whatever it is. So 2 minus a over 3, right? So 3a squared minus 12 over 4a squared minus 9a plus 6. And then plus 2 minus a. Yeah, we should do this no matter what because apparently that thing has literally 3 roots. So this is 2 minus a over 3a squared minus 12, 4a squared minus 9 plus 6 plus 2. I am first going to rewrite it because it's too much of a coincidence for the linear function to match the fraction in 3 parts. Yeah, that is actually too much of a coincidence for me to believe that. And so something happens when something should happen when I do this. I'm not sure exactly what, but it'll... Okay, so when I expand, minus 4a cubed plus 8a plus 17a squared minus 24a plus 12 plus 3a squared minus 12. So predictably we get God. What's the error this time? Ah, freaking. It's gonna be a long day. Alright, and the point is that this top factors, right? Minus 4, a minus 2, a minus 3. Okay, so this is sort of the correct form, I think, to write it in. We would like to show the inequality. Arton, I don't think I ever took a class from Arton. So if a plus b plus c equals 6, then cyclic sum of a minus 2, a minus 3 of a 4a squared minus 9a plus 6 should be non-negative. So this is sort of the right way to write it, I think, because now you can see all the equality cases. Okay, so that is something. Oh, now what do I do with this? So when is this? This thing is only negative for values of ABC between the interval 2 and 3. Those are sort of the critical points. It's between 2 and 3. So actually there's a lot of cases for which if you don't have a value between 2 and 3, the function's already such a positive period. So I wonder if I can just do cases based on like whether a number is bigger than 2 or something like so silly like that. Certainly one of the numbers is less than or equal to 2, no matter what. Could I have... What's the behavior of the function if a is like close to 0? That eventually cuts off. I wonder if I can just fudge the bottom or something. Can I? Can we smooth by Karamata now? Well, all I did was apply linear transformation, so I would be surprised. It won't change any of the inflection points. But I want to like simplify the denominator somehow. You want to smooth? Yeah, I have a smoothing feeling as well. So the smallest number is at least 2, and the largest number is... Isn't this just Lagrange? What's Lagrange? Oh no, you want to use Lagrange multipliers? Oh, Jesus Christ. I guess we maybe could have done that from the start, actually. Lagrange is cringe. I've been looking. Oh, that's not good. There's non-trivial local max. Oh, if there's non-trivial local max, that's not good for smoothing either. Unless we're like, you can't change it by just epsilon. You need to like... Shouldn't tangent line tricks still work? No. Why would tangent line work? you would need the function to... In order for tangent line trick to work, the function would have to be like just a line or something, which doesn't look right to me. Here's a random thought I had. This is a boatload of nothing. So if I have a fraction, I should be able to, let's see, if the top is positive, then the fraction decreases if I add a positive thing. Right. So I can add on multiples of a minus 2, a minus 3 to the bottom. This inequality is true for every constant k, because if a is at least 3, for example, then I'm adding something to the bottom. So my question is, can I add like some combination of a squared minus 5a plus 6 and 4a squared minus 9a plus 6 to do something? I don't know what that something would be. How did you get it? You add 2 minus a, so it's the derivation on the left. When I add this 2 minus a. So this is true for every k. And I'm trying to think if there's like a value I can add that will make this thing work out more nicely. I want to say there isn't. Lagrange tells you they are all equal. It does. Does it? Alright, okay, let's pull Lagrange. So alright, what does Lagrange multiplier say? We're going to apply over the compact set 0, 6 cubed with domain with constraint a plus b plus c equals 6. So in order for this to work, you would require, the boundary cases look annoying, but also the boundary case seems like a one variable inequality or something, if you phrase it correctly. So the gradient is non-zero because it's actually the constant vector 1, 1, 1. So alright, now that means I need to differentiate this function. Oh, Jesus Christ. Okay. So if I apply to the original function, 9a squared minus 4a plus 36, 4a squared. Okay, so the constraint is that these three things are equal. Is it worth, like, won't learn anything by doing Lagrange multipliers? Yeah, probably not. I don't know, but I don't see what I'm supposed to do. Like, I have it down to this form, which I think is pretty particular. I don't see how to proceed further from there. I won't learn anything anyways. Well, someone has a suggestion for what to do with the equivalent form. I'd like to hear it, because I don't see how to push this further. No. No, this function is... Yeah, Jensen won't work because it won't preserve equality case. Bounded with a piecewise function. We need to bound this by something. I can't just use a random linear function. Stop. I stopped already. This problem is a non-LM solution. Well, I mean, it better. Unfortunately, my brain is fried from China TST, so I might not find it. But we can try. Can I do anything with this? Like, I want to make... They're just post USA TST. Someone solve this for me and tell me if the value of k is positive. Playing into Warfare Alpha. Am I the only one still trying the problem? 24k squared plus 6. Oh god, it's not rational. Alright, never mind. Damn it. Okay, that's probably not worth trying then. Is there any value of k for which something good happens? I guess that's what I'm curious. Amazing. I guess the upshot is like you can kind of do dumb things on the bottom now. You can do inequalities, which like what polynomial inequalities hold for? Well, actually that's equivalent to what I was trying to write. Yeah, it's equivalent to adding multiples of a squared minus 5a plus 6, so I won't do anything special. I don't know how I'm gonna get this. Postman 3 times in 4 weeks is a world record. Why would you do this? This equality case at A. Well, I mean, we're assuming A, B, C are non-negative anyways. Yep, I don't have anything. Now see the sun. I really want to apply inequalities to the denominator, but this doesn't work unless a is outside the interval 2, 3. Yeah, so far nothing's happened. The only idea I've had is that you can add multiples of a squared minus 5 plus 6 to the denominator. Like that's a legal estimate. But I don't see... I didn't find a value of k. I didn't find a multiple that looked like it was useful. Yeah, we also decided Lagrange multipliers was not the right thing to do. What if we try casework? I had the same thought, like, I think in principle maybe we can do something. So there's either one negative thing or two negative things. And actually I'm surprised that the 2, 3 is the interval I think you care about. So if there's either one negative term or two negative terms. And then you can try to say something about them. So if one negative term, so suppose that's like a is in 2, 3. And b plus c. But also, so in order for this to have only one negative term, you would need like a is in 2, 3, and one of them has to be less. There's always one thing less than 2, but let's sort them actually. So a less than b less than c, and hence a less than 2, less than or equal to 2, really. So either you can have a case where if c is less than or equal to 3, then if b greater than 2 or if b is less than or equal to 2. And then you'd have to do something. I don't really want to do it, to be honest. What if we agree the inflection points of this function were... does someone want to compute the double derivative for me? Because I don't. So if b is also less than or equal to 2, then c is like... Well, we're only worried if c is less than or equal to 3. It seems really annoying as heck though. Yeah, I think, oh, I feel like the smithing would just be annoying, honestly.
Rather, it's about
Yeah, I don't know. Everything seems like it's going to involve some calculation, so I think there's something I'm not seeing. Yeah, doing the double derivatives is not. Yep, I don't know. I don't have anything. This function is not non-negative. But it's really almost non-negative. It feels like it's like barely not non-negative. But I don't know how to make that into a useful form. I wonder if I just stupid bound it. Probably not. Like, it's really barely non-negative by like any metric. So for like 2 between b between 3, for example, b minus 2, b minus 3, like this thing I can this thing, it's like how bad can it be? So if b, we want like b close to 2, so this is like b minus 2 and then times something, right? Which is Jesus freak, there's a car outside that is just honking its head off. Yeah, like for, let's say for p between 2 and 3. On the one hand, if I'm close to 2, yeah, between 2.5, then this guy is at worst. This is at most 1. This is at most 2 and 5/2. And this numerator is like okay, so that God, what is that stupid card doing? So for b close to 2, this is at most like 4b squared minus 9b plus 6 Can someone... Okay, I should write that in some form. 4x squared minus 9x plus 6 when written in like standard form is 2x minus... Jesus Christ. 9 quarters squared. It's like 81 over 16 plus 15... This is correct, right? 81 over 16, 96 over 16, 6. 2x minus 9 quarters, 4x squared minus 9. Yeah, okay. So written that way, this is like 1, the 5 halves, and on the bottom, that denominator is always at least like something. Yeah, well, if the apex is at 2.25 to... Right, so it gets... Right. So b equals 2 is the smallest it will get. And when b equals 2, that thing is equal to 16 or 4. Well, I think right now my intuition is this inequality is barely true, like barely failing. Like the problem is that there's some values for which it's negative, but when it's negative, like it's like barely negative, like you can barely see it. Like it's like only a little bit negative. And my feeling is that this should prevent it from... I should be able to like do some piecewise thing like this and kind of force it all the way through. So this is if b is close to 2, and I want some bound if b is close to 3. And this time, you use b minus distance from 3. Okay, and for 2.5 between b and 3, it'll be some lower constant, right? So b is... Actually, the b is a little bit bigger. So 2.5, 3... Hang on. I messed up the earlier one. This is 2. Oh no, this doesn't sign. So this b is at least most 3. And b minus 2 is at most 1. But then the bottom is like 25 plus 6 minus 22.5. So like 8.5 or something like that. B minus 3. Ah, frick. Maybe I shouldn't have picked the midpoint. It's okay. I don't think this bound should matter very much. I'm gonna hide this. For the record, I've almost never have done a thing like this, which is why I was kind of hesitant to do it, because this is not what I'm used to either. But this is 3 over 8.5, which is... Did I get that right? Minus 2.22.5. 25 plus 31, 8.5. Here it's like 16, 2, 4, 3, 1, 3. So this is 6 over 17. Which is, so this is this bound is about 0.6, this bound is about 0.3, so this is it. So there is an effective constant of 5/8. That's fine. So we can, for if there's a negative term, we can bound it by like. Actually, if both things are, if B and C are both like slightly under 3, then A is like pretty close to 0, right? Three, 3, 0, we agree was an equality case. So why, when A is close to 0, how close? This is annoying as hell. I hope this works. Okay, so that's the bound here. So what cases am I looking at? Are there any cases I can resolve right now? So I think the easy case, quote unquote easy case, should be if there's only one negative thing. So this means A is always less than or equal to 2. That much is clear. So if there's only one negative third term, so let's see, A is less than or equal to 2, then that negative term should be B, and then I have a C term here. So let's see. Yeah, this case should not be even close. And I should just be able to solve. I should like. So if B is close to 3 versus if B is close to 2. So if B is close to 2, then the worst situations are A close to 2. Maybe I don't even care about A. But if B is close to 2, then C is at least something. Well, if B is close to 2... This is very sad. What happens if I write this out for large things? If I do division algorithm, what do I get? Like basically these constants seem like they should be too small. Okay, actually, let me do the following. In particular, we have f of b is less than or absolute value of f of b is bounded below, bounded above by 5/8 of 5/16. I think the true bound is a lot better than that, but the function never becomes more negative than this number. Yeah, this is a strict inequality as well. shoot. No, I don't think this can work actually. Because the problem is if I have A, B, C all close to 2, and then I nudge B and C slightly positive and A slightly negative. Yeah, I don't think this can work. As written, I don't think this can work, and I might have to do like a piecewise tangent thing. Okay. Alright, time to differentiate. So I think the following claim should be true. I'm convinced this should be the case. Claim, we have x minus 2, x minus 3 over 4x squared minus 9x plus 6 is at least the min. Sorry. It's at least some piecewise function. So this will require me to take a bunch of derivatives. Freaking. Oh, I don't want to differentiate. Okay, I have to differentiate. So f prime of x is equal to 4x squared minus 9x plus 6. Is the solution nicer than this? Probably, but I don't know what to do. Yeah, I don't want the exact minimum. I only care about getting the slope of the tangent at each point. X times x squared minus... Okay, I hope I got the quotient rule right. And if not, I'll find out very quickly when the sign completely doesn't match. Okay, so this is a thing, and oh crap. No! Okay, so we're going to bound this. So let's take that derivative, 3x squared minus 10x plus 6, and then 8x minus 9. Okay, so I need to now plug in 3 values. I'm plugging in the derivatives of 0, 2, and 3. So for 0, this is 36 over 36 equals 1. And for 2, this derivative is, okay, 12 plus 10, 8 times 4, 16, 22, 4 minus 8, 12. Oh, ha, this is nice. This thing is always 0 for all 3 of those points. Ah, good choice. So it will be 8 over 4 is 2. Wait, these numbers are very clean. F prime of 3 is then... Wait, oh, this is just 1. And then 3 is 81. 3 is a large one. 77 against 9, 36, 33. Oh, wow. Wait, why are these canceling so nicely? I don't expect it to cancel that well. Really? They cancel that cleanly? Can someone check I didn't screw this up? Because this seems too good to be true. Yeah. Yeah, okay, one of the numbers is definitely wrong. This is 3 over 30. Wait, what? 3x squared minus 10x, 9, 27. Yeah, sorry, this is where I don't know where I got 77 from. This should be 9, 27, 3 over 3 over 15. Wait, now I think I'm just hallucinating now. 4, 12, 18, 8. This is 1/5? It's 1/5. Okay, whatever. So someone please check that I got the derivatives right, because otherwise this is going to be a whole lot of nonsense. F of x is, we have, it's, okay, so between the interval like 0 to 1, so it's at least, it want to be at least x for x up till the intersection point, 4/3. Then x minus 2 has a slope of, wait, f prime of 2 should be negative, right? How is it not negative? Sorry, this is, what, I don't know what I'm doing. This is minus 2. Why is every value I plugged in wrong? I swear I haven't gotten a single run right. 4, 16. Okay, minus a half. F prime of 0 is negative 1? No, there's no way. It's increasing when... Okay, so we're going to minus a half x minus 2. And then 1/5 x minus 3 for... I don't know what this is for. You made a mistake. No, I not. Okay. Please assist. I cannot compute. Okay, so... Okay, so this will be true for x at least. Let's just say 4/3 to x at least like 5/2 ish, 2.5. And then this is probably true for x. This will be true for all x at least too, really, to be honest. F prime of 2 is not minus a half. What's f of my 2? It's minus 2 over The derivative of minus 9x is not... oh, that should be 9. It doesn't matter, but, because when I plug in x equals 0, 2, 3, those all vanish anyways. Wait, is it not minus 2 over 4? It was 2 before, minus a half is the right one. Okay, so it is minus a half. Okay, yeah. Alright, so this is a claim. 1/5 x minus 3. God damn it. I can't type anything correctly. We got this claim by computing the derivative. But the claim is for x, we have something that looks like this. This probably will be easier if I draw a picture. So let's draw a picture to illustrate this. Incidentally, since I'm typing this in asymptote, I can actually use the real diagram. Real f, real x, return x times x minus 2 times x minus 3. F from 0 to 6 operator ... Yeah, because I'm too lazy to get out my iPad to draw a freehand. Okay, but anyways, so yeah, here's a diagram of the figure, and then we are bounding it above by 3 lines. So there's a line from the origin to 4/3, comma f of 4/3, or actually just 4/3, and then down to 2, 0. Where are the axes? I didn't draw them, sorry. Oh crap, something's wrong. Did I misdefine the function? Wait, that's not good. Hang on. It's minus a half. Oh, sorry, so this should be x to 2/3. Right? Sorry, so this should be 2/3, 2/3. Incidentally, now I know that 4/3, 4/3 is on the cubic or something. Right, so because it's a derivative, at least locally, it should be a tangent. And then, okay, so we set up to 5 halves, right? Actually, when is minus a half x minus 2? Where do those two lines intersect? I'll just take the intersection point as the other endpoint. So these meet at 16/7. And at 16/7, the point is minus 1/7. And then back up to 3, 0, and then to like, I don't know, 4. Okay, so here's the diagram of our approach. The graph f shown Let me not put arrows. No! What? Why did it crash? Extra alignment tab. Oh, crap. Alright, so we don't. The tangent line trick does not work. However, this might. We will bound the function above by this wonderful piecewise curve. I will draw the axes now, I guess. 0, 0. Yeah, so that's your picture. Okay, so the inequality should be true because, like, you know, you verify it by doing the factoring and whatever, and it should work in the intervals. So this should be something you can check by hand. And now, now you can do smoothing on each of the intervals. Like within each interval, I can, what are the blue lines? The blue lines is this function. So this is triple tangent line trick at 3 different points with the piecewise thing. And the reason this works is because it's just like this thing is so barely non-negative, or barely negative, that it's like almost anything I do should work. So I will do the, you know, most heavy-handed thing possible. And okay, so because I did the tangent line trick, and I will, you know, you can expand and check that it's fine. So now you can do smoothing, because if I have a negative number, if I have something in here, well, actually, shit, this is really annoying. Well, okay. The claim is that if ABC are variables with sum 6 on the blue curve, then the sum is also non-negative. And now I can prove it because it's a it's like a piecewise function. I can smooth it pretty well. This part is convex, so I can squeeze these until they're at the minimum. Yeah, this absolute value part is convex, so I can squeeze them together. And oh my god, please no. So it's convex over this part for x at least 2/3. So actually n-1 EV applies, and now I'm doing n-1 equal value principle on the blue function, which is really easy to do. So you can assume 2 of them are equal, and the third is like maybe up before here or something. Yeah, if I have 2 things here, then everything's non-negative. So you can assume there's 2 things in this blue branch over here. I squeeze them together until they're the same value, and now I just need to check the inequality for, yeah, for this thing. But for things close to here, if both the points land here, it's over here, and if both the points are here, it's close to here, and this slope is more than double. So this works. By n-1, this is the dumbest thing I've seen all day. But, here's the solution. We did it! Just before midnight, too. I was worried that we were I'd have to stay up past midnight today. But, wow. This happened. This wonderful black magic solution. This is not even black magic. This is just like, it's so... I don't know if this qualifies as black magic so much as like, Look, there's no magic. It was like, well, I think the magic step honestly was writing it in this form. This is the part where it was like coincidence. But you know, the idea that tangent line trick really basically should work. You know, it's sort of it does what it should. Alright, so I'm not going to write out the other part, but... Okay, yeah, I want to see the official solution, because I feel like it's... Okay, so... I'm thinking a man for a bit. What the? Okay, so it's not actually that different from what I did. Okay, okay. Alright, so I didn't miss... I didn't super miss something. I see. So you did the tangent line only at 2 and 3. You didn't use the 0 case, so you did it twice. I see. The tangent line hits at 1/2. So it'll work as long as... Okay, and if they're both less than 1/2, this estimate is good enough. Oh, okay. That's fine. I see. The point is that this blue line intersects here at 1/2. So tangent line almost works anyways, and the only time it doesn't work if you have something here, and in that case this blue line is better. Tangent line. Interesting. Okay. Shout out to the n-1 evil chin principle, apparently. Alright, well, okay, time to do the write. This write-up is going to look really silly. Wow. So I learned something new today because I didn't know this was a thing you could do either. But like the thing was that this thing was so barely negative that I was just like, come on, this has got to work. Okay. So Christmas AML. No, it's called n-1 equal value principle. It's not evil chin principle, okay? Okay, so... (2/3) 16/7 and 1/5 x minus 3 x at least 16 over 7. Thank you, Conch Shell, for the follow. Okay. Does anyone remember how to draw axes in asymptote? Like with like ticks and actually it doesn't matter. This picture's good enough. Import PGF and use that. Okay. Let's see. Oh frick, I meant to dot it, I'll label it. Okay. Claim if f of x is at least g of x for all, well, we have for all hex in 0, 6. Proof. Direct calculation. It becomes direct calculation. It's fine. Hence, it suffices to show if min ABC is at least 2/3, then Jensen finishes. If A less than 2/3, BC greater than 2/3, then by Jensen, it is enough to on the convex part of G. It is enough to show that G of A plus 2G 3 minus 0 over 2 is, which is easy. And if A, B less than 2/3, then C is greater than 3, so all terms are non-negative. And this finishes the proof. Okay, the end. Alright, what a night. Okay, let's post. I'm glad I actually managed to get it. Yeah, I started doing the write-ups on the stream because I used to not do it on the stream, and then I just like have like 10 backlogged at once, and I was like, I just never got to it. It was a huge procrastination issue for me. So now I just write it up immediately. Part of the reason is that when I had a backlog, when I got to the thing, I usually didn't actually remember how to do the problem anymore. So then I have to also go and like dig out the video and then watch it to figure out, you know, what the key steps were. And then I was just like, never mind. Why don't I just write it up after I solve it when it's still fresh in my mind? So yeah, now the write-ups are done on stream.